All right, now this is starting our second recorded lecture, continuing our discussion about the structure of an atom. And I wanted to start off with this, coming back to this atomic diagram here. So I want to go more in depth on these subatomic particles that we had discussed before. Starting with the middle of the diagram. The middle of the diagram, or as you might commonly call it, the center, is referred to in the atomic model as the nucleus. And the nucleus is essentially a tightly packed form of positive and neutral subatomic particles. So here in the example of the carbon atom, the center, or the nucleus, is filled with protons and neutrons, and they are tightly packed together in the center. Conversely, there are also layers, almost like rings protruding from the nucleus, and we call those layers valence shells. And the subatomic particle that occupies those valence shells is the electron. And the amount of rings will vary at times depending on the size of the atom. But essentially, we can think of this dense core, if we're thinking of the nucleus as a core, surrounded by layers, think almost like a jawbreaker candy, how we have layers of sugar building up on the outside. That's similar to what the structure of an atom is like. And so if we go, we'll come back to this analogy here in a moment, but there's some key vocabulary terms that we need to cover. And I'm going to type in this table here, referring back to our notes. So the first subatomic particle, sub, that prefix meaning smaller, so subatomic particles are smaller than atoms. The first one we refer to as the proton. And the proton overall has a positive charge. So if you look back at this diagram, the location of the proton is in the nucleus. And its mass, there's kind of a funky naming system that chemists use to designate the mass of a proton, but it's essentially one atomic mass unit. So we just say it's 1 unit of mass. Its overall charge, because it's positive, is +1. And the functional role of the proton is determining the atom's identity. And I'll elaborate on what that means with a simulation in just a moment. But the second subatomic particle is the neutron. And the charge of the neutron, it sounds just like it's named, it's neutral. Whereas its location, remember, it is also packed in with the positive particles in the nucleus. Its mass, similar to the proton, is also 1 atomic mass unit. And its charge, because it's neutral, it has a charge of 0. And the functional role of the neutron is not to play a role in the identity of the atom, but rather it's to add extra mass. And the last one is the electron. The electrons are the particles that are found in the valence shells, or those rings that are protruding from the nucleus. And electrons have a negative charge. So their location is in the shells. Unlike protons and neutrons, they have an extremely light weight. So they are actually said to have zero mass, which sounds a bit funny, but that's just the way it is. And the charge, like we said, it's negative, so it's a charge of -1. And you may remember at the end of the last recorded lecture, we said that as atoms gain or lose electrons, it plays a role in how they have affinity to other atoms, how they link to other atoms. And that's really the functional role of electrons. They are involved in linking atoms together. And in chemistry, we actually call the linking of atoms together as bonding. Those are chemical bonds. Now, if you're looking at this thinking, how am I going to remember all of this? For at least two of the particles, the name is similar to some of the properties. So the proton, P for proton, P for positive. For neutron, neutral, the charge, sounds just like the name. Electron is where it deviates a little bit. But just remember that electrons have a net negative charge and occupy the valence shell of the atomic model. And I want to go into a little bit more detail about these functional roles. So there's a university out in Colorado that has all these very helpful simulations for science online, and it's free, accessible online. And so this one here is for building an atom. And I think it's really helpful if you wanted to look this up and play around with it, just to give you an idea of how these different subatomic particles affect the identity of an atom. So say we start out with one proton. It identifies, because it has one proton, its identity is hydrogen. Now, if you'll remember, I said that protons, changing the number of protons will change the identity of an atom. So if I have 2 protons, that changes the identity to helium. Now, how about if I add a neutron? A neutron has a neutral charge, but it will increase the mass. So if I add a neutron to the nucleus of this atom, it doesn't really change anything, right? It would change the mass. It changed the mass to 3. Now that if I took it away, it would have a mass of 2. Add it back, I've got a mass of 3. The net charge, however, is still +2 because I've got the +1 positive charge from 2 of these protons and the 0 charge from the neutron that I just added. Now let's say I add an electron. And I actually see when I tried to add it to the nucleus here, it rejects it, rightfully so. The electron is supposed to be in the outer valence shell. And you'll notice as I added that electron, our net charge dropped by 1. Now, if I add 1 to the other side, it's now neutral. So this is still helium, but because we've added this neutron and we've added these electrons, the mass number is 3, but the net charge is 0. Now let's say I add another electron to the second valence shell here. Now the net charge is -1 because I have 2 protons, a neutron that's worth 0, and 3 electrons, which are worth -3. So overall, that leads to a net charge of -1. Now let's say now I want to change my identity. That's where we add this proton. And now it's no longer helium. Now we're looking at lithium because we've changed the number of protons. So I would definitely look at this atomic model simulator if you have time. I think it really enforces the concept well. All right, and another analogy for each of these subatomic particles is a concert. So let's say you'd almost take a slice of this atomic diagram and you depict it as a stage. And the actual band, so the actual identity of the concert, let's consider that the proton. And we'll call the backup singers neutrons. And the audience here will be electrons. And I'll pull up a sticky note here just to take some notes. So we'll say the band is the protons. And we think of that as the identity of the concert. We've got backup singers and dancers. And those are depicting the neutrons. And then we have the audience, and those are the electrons. So to further explain this analogy, so say you have, like, let's say back in the day you went to go see a Nirvana concert. And in the 90s, when the band Nirvana disbanded after Kurt Cobain passed away, now they're losing a couple band members. The band has disbanded. So we've removed a couple protons. That's changed the identity. So now it's just the drummer, Dave Grohl. And he goes on to create the Foo Fighters. So we've changed the identity of the concert here because it's a different band now. It's a different atom. However, let's say you make a change in the backup singers and the backup dancers. Even though you're changing that number, even though you may be changing the mass of this center here, you're not reclassifying the entire concert, because, like, you don't specify, oh, I went to go see Foo Fighters and there were 3 backup singers and 3 backup dancers or 2 backup dancers. It's a more minute detail in a sense, similar to the number of neutrons in an atom's identity. Yes, it changes the mass, but it doesn't change the overall identity. Now the audience, they are the electrons. Because they have a negative charge, those electrons never touch the singer at the center. The negative charge is never touching the positive charge. And similar to valence shells, these stands, or these outer shells here, can hold a certain amount of people or a certain amount of electrons. So two people can sit in the front row, but maybe additional people could sit in the second, third, and fourth row. Up to 8, actually. Up to 8 electrons can be held there. So this is all kind of similar to a concert in a sense. And if you have any questions about this analogy, please feel free to let me know. But I think this is a good way to let it stick. All right, so moving on to more vocabulary here. So the atomic number is the number of protons. So each element has a different atomic number. That's how we differentiate them, right? So say we're looking at the periodic table. Right, so hydrogen, what differentiates hydrogen from helium is the atomic number. So we start out with 1, jumping over helium to 2, lithium has 3, beryllium 4, and so on. So once again, just to really hit this point home, if you change the number of protons, you change the atom's identity. And the vocab that we're about to get into you may be a little confused. And if you do, please feel free to put a note in the discussion board for this week with any clarifying questions you may have. But for now, we will power through it. The mass number. This is the sum of all the protons plus the sum of all the neutrons. Okay, so why do we not include electrons? If you look back to this table that we just filled out, remember, electrons have a mass that is considered 0. So the only thing that we're considering in the mass number are the only 2 subatomic particles. Mass. Atoms can gain or lose they can gain or lose electrons. So atoms can gain or lose electrons without changing their mass number. However, what happens when we start, if the purpose of neutrons is to add extra mass, what happens when we change the number of neutrons? And so this is a new term, this is an isotope. So isotopes are atoms with the same protons, but a different number of neutrons. So atomic charge is the number of protons minus the number of electrons. And why is that, right? So the number of protons, remember, is representing the positive charge, and the number of electrons is representing the negative charge. So you need to take away a negative charge to get the overall atomic charge here. So here are the only 2 subatomic particles involved. Involved are those with charge. Atoms can gain or lose electrons. You'll remember me saying earlier in this video, that's how they initiate that atomic linking, or the bonding as we call it. So atoms can gain or lose electrons. And electrons are a variable subatomic particle. And so just to really hit this point home, if you change the number of electrons, you change the atom's atomic charge. But ions are when you change up the number of electrons. But if it's a neutral atom, we say if the number of protons, so to be a neutral atom, the number of protons has to equal the number of electrons. And for ions, that's if the number of protons does not equal number of electrons. So in other words, it doesn't have a neutral charge. So now, if we're tying all of this together, we want to show isotopic notation. And I have an example of this here. So this is magnesium, and essentially the structure, like the isotopic notation structure, is to have the mass number in the top left corner and the atomic number in the lower left corner. So the atomic number of magnesium is 12, the mass number being 22, and the charge for isotopic notation will be in the top right corner. And this makes sense, right? So if we have an atomic number of 12, that means it has 12 protons. However, we know it doesn't have, we know that the total mass number is only 22. So that means there's 12 protons and 10 neutrons. So these 12 positive charges, this positive charge of 12, there's probably 10 electrons in the valence shells out here, leading to a net charge of positive 2. So this, if you want to write this down in your notes, this is what the isotopic structure looks like, the notation. So how are elements organized? So the periodic table lists all elements, and every element has its own box. So if we remember the periodic table, okay, so every element gets its own box, right? And it's sort of sorted by atomic number. So we have the low atomic number starting up here, and it tends to read like a book. So you're reading from left to right, and then so you jump over to helium, and now you want to move to the next page. So you start over down here. You're reading down the lines almost. So you jump from helium over to lithium, make your way over to neon, and then jump down to sodium. And you're continuously reading these rows from left to right, moving from the top down. So if we go back to our notes, so they're organized by atomic number, and they are filled in from left to right. And it treats elements as if they are neutral. Or in other words, if the number of protons equals the number of electrons. And here I need to probably insert a text box. So what I'm trying to do here is number each of these arrows and the aspect of this labeling that it's responsible for. So the first one is the atomic number. So the atomic number of copper is 29. So there are 29 protons in the atomic model. 2 here, so 2 is the atomic symbol. You can think of the atomic symbol almost like a nickname. So my name is Copper, but my friends call me CU. So it's that type of deal. 3 would be the full name. Makes sense, right? The full name here is Copper. And the fourth aspect of this diagram, we actually won't use in class. So I will spare you the extra concepts here. So we won't use in class, so you don't have to worry about this fourth number here that you're generally seeing on the periodic table. It is the atomic weight, but for the purposes of this class, you won't have to know that. So that is where we will stop for now, and we will have a problem set so you can reinforce all of this information that I just overloaded you with.